Greetings, 216ers. This is Professor Kaufman, and what ensues is our final project overview video for the semester. The project's divided into two distinct problems, and I suggest that you work on them in order. In part, that's on account of we've covered all of the material required for completion of problem one. That includes things like pointer arithmetic, making use of structs, pointers to things, as well as the system call mmap, which is required. It builds a small implementation of a heap so that you can have your very own version of malloc and free there. And I'll say a few words more on that as we get into this. The second problem is independent, so ostensibly you could work on it first if you like. However, to get full credit on it, you'll be required to make use of threads. And that's our final topic of the semester, things we'll be talking about over the course of this lecture week and next week's first lecture. The lab that's going on right now, Lab 13, is a great model for how to go about the structural aspects to that, although there are some tricks you'll have to pull out there. So I'd recommend completing problem one first, and then once you've got thread stuff from lecture under your belt, you'll be in great shape to finish up problem two. Neither of these is particularly long, and due to the somewhat tight time constraints that we have to complete it, you're provided with a template in both cases to fill in code in select spots. It's not so much that every function has long instructions, like just a line here, line there. It is, though, that you won't have to create any files. So if you look at the manifest over here, there's an lmalloc.c, which is partially complete, and that's where you'll be writing all of your code, filling in some function definitions to complete your implementation of a heap, as well as sumdiag optim for optimized. This is short and just has one function that you'll want to write. You can take that in several versions, and potentially you're fine to make each version a little bit faster than the preceding one. We'll look at both those things in a second. So the usual regime is in place. There's a division of credit between automated tests and manual inspection. The grading criteria for both problems are listed in the project specification in the commensurate sections here. So let's get into it. One of the nice parts about the project is you can download and immediately compile the code, I think, if I remember right, if I set things up right, and it should enable you to run the tests. You don't expect to pass any tests right out of the gate, but it's useful at least in that the setup is pretty minimal. We can do that right now. I'll grab over here this P5 code, and I'm not logging in Grace, but I don't necessarily have to be. We'll talk a little bit more about that later. Use a wget to grab this down. Which over here, if I refresh, I should have my P5 code.zip. If I unzip that here, it should create a P5 directory, and you'll see various things in here. Problem one deals with an lmalloc system, and most of the code that you'll write is in lmalloc.c, which is here. And again, problem two is an optimization problem, so that's sumdiag optim.c. There's some other files that are associated with that, but you'll write most of your code in here, along with a few other tidbits. But if all is well, I should be able to just type make. I got to change into the correct directory for that. Make, and everything compiles, and I can even do a make test, and probably everything will fail right now, but no matter on that. All right, so let's talk about this first problem, what it entails. You're going to be building a heap, and this is a good exercise in understanding how computer memory is just a bunch of raw bytes, and just with the right manipulations, you can overlay a more convenient mechanism to dole out those bytes, and that's generally what malloc systems do. And they have a very simple interface. You have a malloc function and a free function, and to that end, you can drop in different implementations of malloc systems and explore potential performance benefits that you might get out of them. So the particular implementation that we're going to do is only of modest sophistication. It's called lmalloc, which is Spanish for the malloc, or more properly, the EL is short for an explicit list. That means that each of the blocks, whether they've been allocated and are in use by a call to malloc, or if they're available because they've been freed or never allocated, they'll be tracked in doubly linked lists. So there'll be an available list that says here's all the chunks of memory that are available for allocation and could be used to grant a malloc call. And here's all of the in-use blocks that we've previously returned a pointer to them. And so the users ostensibly plop some data in there, about the user being the user of the library here. They'll remain in that used state until they're freed, as in someone calls free on it. The picture of the heap that I like to keep in mind is down a little bit lower, so I'm going to scooch past a few of these diagrams. It'll look like this. So this big chunk of memory here that's got some colorful elements to it is the heap. It's one contiguous block of memory. And if you inspect the heap setup, this is just a memory mapped page that was in there. And it can be extended by memory mapping some more pages to create a continuous line there. Now the colors over here mean a couple different things. You'll see the little blue things here. These are what we'll refer to as headers. Each block of memory that's been granted the user, so they have some user pointers, they point to these gray areas over here. They're preceded by some sort of a header that tracks information about how many bytes are right here and what state they're in. The green parts are a footer, an L block foot T, an L block head T over here, which also tracks how big the little gray area is. You notice there's some gray areas and some yellow areas, and the astute observer will see, oh, all the gray areas are preceded by a blue thing, a head that has a U in it, whereas all the yellow ones are preceded by a blue block that says A. And these are short for used and available. And these are tracked in a couple different lists. So if you were to linearly stand across the heap, starting at a low address in the heap, the beginning spot for it, you'd see, oh, there's used block, that's 256 bytes big. And after that, there's an available block that's 22 bytes big. There's a used block here that is 38 bytes big, and one that is follows that's an available block. And generally, this should track used, available, used, available, used, available. This is one of the used, available with potentially used blocks in a row over here. There should never, if you're maintaining a variance right, be two available blocks in a row, and we'll talk about more about why that is later on. The header, that is this blue thing, also tracks the size of these, and we'll talk a bit later about why there's some redundancy if the head knows is 256 bytes, and the foot also knows the thing that precedes it is 256 bytes. The thing I want to call your attention to that's apparent in this picture, though, is that if you were to look at only the yellow things, they're sort of discordant. But there's a globally available list, a doubly linked list, that has links to say, if I wanted to search through the available blocks, for instance, someone's asking for one of a specific size, then there'll be within this L control, which is a list, L control is the global data structure control, a list called avail, and it has a node called begin that will take you over here to the first available node. And if you were to track some internal pointers to those to find the list next, that would skip across the heap to take you only to the yellow blocks, the available space that would be used to grant mallocs. Similarly, there's a used list. So within L control is global data structure. There's a used list. It has 4 elements in it. There's 1, 2, 3, 4 gray blocks up here, 3 of the yellow blocks, etc. And if you were to follow its beginning pointer here, you'd start right at the beginning of the heap because that one's in use. And these little arrows above here are meant to track like, oh, this points both forwards and backwards to the next available one, or I could go backwards to this previous used block, as well as sort of scan ahead through the used. I don't know of any major reason that you would track a used block list. It's just useful in terms of debugging and demonstrate a few things that are interesting about the system. Generally, the reason that you track available lists like this is that the central idea when fulfilling a malloc request is search through these yellow blocks only and find some block that has enough space to allow. For instance, if I said, hey, malloc me something that is, 60 bytes big. The implementation for malloc will look something like this. Start at the beginning of the available list. I'm looking for 60 bytes. And I see, this has got 22 in it, so this isn't big enough. Let me skip over to the next available block. I'm looking for 60, and this is too small. And I'm going to skip over here. 60 might actually work out for this available block, which has 100 bytes in it. I want to draw your attention as well to the fact that the user pointers, the pointer that's actually returned from call to malloc or free here, it actually points at these gray areas that are in between the little header footer things there. And so as long as the user says, hey, give me 38 bytes, and you return a pointer to this gray spot, and the user stays within that 38 bytes, all is well. If they happen to go over that, then they'll clobber data nearby in the heap and thus corrupt some of the data that's in here, nixing this footer so that it reads wrong, but it doesn't have 30 in it, potentially mangling this available header block here to indicate this is no longer available and it has wrong pointers to things that aren't over here. And so generally this is why it's important when dealing with malloc space not to go over. You ask for 10 bytes and you stay within that 10 bytes. As generally heap management like this will plop down bytes that are right next to the user data that's present here, and going over those bounds would cause trouble. Okay, so let's back up just a little bit and start talking through some of these data structures. So I mentioned that there is a header and a footer. And with a little bit more detail, there's a picture of one down here, along with the structs that describe these two things over here. So you'll see up top that there is a block along with a size for that block and a state for it. And this state is generally one of either available or used. These print out as like an A or a U, but there might be a few other things encoded in there. We'll see as we move ahead. But then there are also linked list pointers to the next and the previous blocks, not immediately adjacent in memory. So we'll talk about there's this distinction of like, for this yellow block right here, there's a block below it. So that's below it in memory. As in I went to a slightly lower memory address that's over here. If I went above it, there's a block that's next to it. But there's also a next and potentially a previous node in the linked list that are associated with these. And that's what those pointers up here are meant to. If this is block is in the used list, then this would take me to the next used block. The previous here would take me to the next previous block. The header or the foot is just a little bit simpler than that. It's just a single number, which is how big is this block over here. So immediately before and after by this blue space and this green space are other things. But these previous and next pointers here, they point to blocks that are not necessarily memory contiguous, so may jump way down or even up in memory, as well as the next over here will point to something else that in this case it's a used block, that's gray and the U over here, and yeah, so forth. So this should give you an idea of like the structural aspect of the general sort of unit of operation within the heap is I grant pointers to something here via a user pointer, but each of those is surrounded by a header and a foot, or a head and a foot. I'm not sure if you can call it what you want. Okay, so in terms of contiguous layout, there's this notion that then in addition to being these lists, there's obviously going to be some block of memory that is above any particular block over here. So I've got an available block here that's marked in yellow. And if I jumped a certain number of bytes forwards from where the header is at, then I'd get to this next header that's over here. That calculation is generally done by the following. So if I have a pointer here to this head, then I want to take the size of this head, so the size of whatever that struct is, which is some number here, a character indicating the states, along with a couple pointers, so whatever the size of that struct is, plus this variable length space here, which is encoded as the size that's right here, so the size of the struct plus this number, by 16 in this case, plus the size of a footer here, that would allow me to jump contiguously forwards in memory to the next header. If you wanted to go backwards, so from this 8-byte block that is in use right now, it could look a little bit difficult because you don't know how big the block preceding you is. However, if you just jump down from a pointer to this header right here, look at immediately preceding it should be a foot. So do a little pointer arithmetic, a pointer to this head, subtract off the size of a foot, that'll get you a foot, and this will say this is how big this variable length space is. So again, subtract off this size 16 plus the size of a foot plus the size of a head, and that would take you from one head downwards. That operation will be somewhat important. It's among the first that you'll have to make use of, that you're provided an implementation of the forwards direction here, of go forwards and say, actually we can pull it up here. In this, let's see, lmalloc.c file, there's a bunch of stuff, and we'll jump down to the point arithmetic functions. So down here, I guess I skipped one, but the L block above, this is provided to you, but then you are required to implement the L block below. This one's interesting in that it uses slightly different arithmetic, so don't copy and paste too hard on that one. And I should mention as well, you get a crash course in this as well, in that you do just a bit of point arithmetic. There's a get footer function that's provided, so given a head, find the foot for it, versus you'll have to implement your own get header given a foot. And you can use diagrams like this one or like the previous over here to say, oh, if I got a pointer to this foot, then I want to work my way down 16 bytes plus the size of whatever head is to get from a pointer here down to the equivalent header there. So this gets you acquainted just a little bit with some of the arithmetic associated with this. It's useful to have some macros, some function-like entities that will assist with the casting involved for that pointer arithmetic. So provided in the header in lmalloc.h is a pointer plus bytes, a pointer minus bytes. There's also a pointer minus pointer. That's not strictly needed in most sane implementations. So I'd expect most of your work will make use of pointer plus bytes and pointer minus bytes here. So make use of those as you implement these first few functions that are required that do just some basic arithmetic. The next phase in this is to deal with the lists that are involved. So the list struct that's outlined in the head has a bunch of parts to it. These include some pointers to the head and the so the first and last node in the lists, as well as how many elements and how many bytes are tracked in that. There's a little bit of subtlety to this, and that's, for instance, there's a block head T that's the actual beginning, which is a sort of dunny node. So this linked list implementation is sometimes referred to as a headed linked list implementation. There's when you create the list, always a dummy node at the beginning and a dummy node at the end. When you can check, there's some special state flags that say, oh, this particular node doesn't actually track any space. It's the dummy beginning and dummy ending block, which makes iteration through the list a lot easier. If you're going forwards, you just look to say, I've got a pointer, and if it's pointing at something with the state ln block, then you're at the end of the list. And you never then have to worry about, as well, dealing with, nulls at the end of the lists. Like, there won't be any nulls because the nodes that you actually work with, if it's the very first actual node, then it'll point to this dummy node at the beginning there. So take that as you go through, as the structure of this is worth a little bit of study and has some subtleties to it. Finally, then, there's a global control structure here that tracks various global statistics about the heap. For instance, the total number of heap bytes that are in use, where it starts and where it ends, just void pointers, so raw pointers to some spot in memory. And then the two lists, the available and used lists, that are each of these L block list type respectively. And so several of the operations that involve, traversing defines like a malloc, find me some number of bytes. It'll make use of the available list and traverse that, starting not at the sort of beginning dummy node, but at the first actual node that's in there. There are a few utility functions provided. For instance, to initialize the heap, it's worth looking just briefly at that code, which makes use here of the mmap function. That function is one that we've discussed in lecture before, and since this is a provided function, you don't necessarily need to mess around with this stuff. However, it is interesting because you'll need to make use of some mmap calls in the very last thing that you do, which is to grow the heap in the event that it needs to. And so you may draw some inspiration from that first function as you get to the last one there. Other things to mention, there's initialization. This is all done for you. And now we get to some of the interesting aspects of the doubly linked list operations. So for those of you who haven't worked with linked lists very much, and in particular doubly linked lists, it's useful just to do a little bit of review in that respect. And I'll say a few words on this here. So in order to unlink and relink list nodes, it's useful to know about this convention, that this bit of code here, node previous, arrow next, which would go back to the previous node and manipulate its next field. You can point that over a current node right now to its next, and likewise go to the next node and its previous field and adjust that, and that will cut a node out of the list. And adding a new list in can be accomplished via something like the inverse of that. Adding at the front might look something like this. It's like, I need to go to the beginning of the list over here and adjust some pointers over that. Set my next field to be the next field of whatever the beginning of a node list is, and then adjust a few pointers additionally here, and that will plop down a node down at the beginning of a list. You'll want to make use of some of those techniques as we get into the use or sort of manipulation of the list in there. And that'll become obvious as we move forward somewhat. There are some block operations here that mess around with the list implementations. So some of these are provided, for instance, the init and the print over here. And some of them you may need to implement yourself. I'm actually having a hard time remembering, so let's look over in the template, like the add block fronts and L remove block. I think that's down over here. See the block above, we did those, block list, print stats are there, and it's, yeah, okay, so you're required to implement the adding something to the fronts and removing something from the end. That's something that can be accomplished mostly through the code that's provided here, but once you get your head around the basic list excising operations, just keep in mind that you'll also want to manipulate some of the other fields of the list that track things like, I'm adding something onto it, so it's going to become one longer than it was. So over here, it's like the length will increase by 1. And the block that's being added on, it has a size like 22 bytes. So if I'm adding into the list, then as well add on the number of bytes there that's tracked in that list. This includes something called the overhead. And it's a good idea to talk a little bit about this right now, as it also pertains to the next function. Every time you create a block in the heap like this, there's some overhead associated with it. So I've got in use right here some 20 bytes or so. However, to get that, I needed to have on hand a head and a foot to track that. The size of the head and the foot, I can't remember the exact, but it's something like 30 or 40 bytes. And so the overhead associated with this block is kind of high. Actually, it's the tracking structs for the head and the foot is actually bigger than the space over here. On the other hand, this larger available block, it also has a head and a foot, and the sizes of those combined are smaller than the sort of allocated space here. So this is a podunky implementation of a heap, and it has a pretty high overhead. So if you're allocating lots of small blocks, then it's not a favorable implementation. You'd probably want to use a different set of techniques. However, it makes it relatively easy to find a few other things up here. And generally we'll refer to the overhead as the combined size of a head and a foot. So this combined total of the sizes of those two structs, which you can find by a size of a block head t and a block foot t. Or if I remember right, there's a pound-defined constant in here that's associated with that. So let me find overhead. Yeah, L block overhead, making use of this constant, which is just pound defined as the size of those two structs. Each time you need to introduce a new block, a little bit has to be shaved off. It's the overhead then of having another block in the heap there. Now, I mention that now because Every time you would add or remove things from a list according to these functions, the commentary says, oh, you're adding a list element on, like add this block there. It'll be the size that the block actually reports, like 22 here or 256, plus whatever the size of the overhead is. So keep track of that as you're adding on to the number of bytes tracked in each list. The main operation then, though, to create a block is via splitting. And so here's a demonstration of a few cases that are associated with that. So the overall idea plus then some individual steps as you go forwards. So this comes midway through that one will have identified, I'm looking to create a block that is 60 bytes big. And for some reason, I've elected this is the block that I'm going to create it from. And it'll be created via splitting. I'm going to cut this 300 byte block in half so that it has two smaller parts, one of which is 60 big, and the other is however much is remaining there. So conceptually, this looks sort of like the following. You'll write this L split block function. And given that this is the block to split, 300 bytes big, what comes out of it is that the initial block that you're pointing at, it will be the one that contains the 60 bytes. And so the size of this block, since this is big enough to split, will read 60. It'll be marked as available because the function split doesn't monkey with the flags at all. And what remains in terms of space will be over here. Now, anybody who's looking at this will see, 300 minus 60 should be 240. But that reads only 200 here because I need to create a new pair of a head and a foot here. And you can see it's sort of in the middle here by separating the 60 byte block that I want to create with the 200 byte block over here. Now, generally, this is done just with point arithmetic. In fact, I've got this space right here. I'll do a point arithmetic and say, I want this thing to be 60 bytes big. So we'll start here. And I'll add on the size of a head to get to this spot here, add 60 bytes forwards, and that would create this 60 byte area right here. And 60 bytes in that's where I'm going to put the green thing, the foot, and mark it as 60. And then if I go up the size of a foot, this is where I'll put another head. Now, the putting part here is literally just do point arithmetic and say, pretend this is now a struct, assign some of the fields to it. Pretend this is now a pointer to a struct, and assign some fields to it. In this case, it would be the remaining space, which was 300 minus 60, so 240, and then subtract off the space that is overhead, which is 40 bytes, so this combined size of a foot and a head. So that leaves 200 left, so mark this as available, plop down a 200 here, go forwards to a foot over here, add a 200 here, and voila, we now have two blocks. And in all likelihood, this splitting happens because someone said, malloc me some space that is 60 bytes big. This is the first block that you could effectively split off to make that happen. Now, there's a counterpart to this that suppose we find a block that's at least 60 bytes big, but it's not big enough to split. The implementation that we'll work on here says no. This block cannot be split because it doesn't have enough space to accommodate the 60 bytes plus the size of a header. So it's less than 100 bytes here, which is the 60 plus 40 for the overhead. And so here, rather than succeed, this one fails. The return value from this split block business is a pointer to the freshly created block up here, or null if that fails. The pointer that's initially passed in, as in like this block to be created, it will be resized to be whatever this new size 60 in this case is. And then a pointer to the freshly shaved off block up top is what's returned over here, or null in the event of a failure. So the general flow of lmalloc then looks like the following. You traverse this available list over here. And so you might see sort of a global heap region. It's like, I come over here. I'm looking for something that's VA big. This one's too small, so I'll skip ahead following linked list nodes to say this one's too small and so forth. Eventually, in lmalloc, the sort of overall function, you search using a find available function that you'll write, which iterates through this linked list until you find a block that is of sufficient size. So in this case, the request is for 60 bytes big, and in that case, we found one that's 300 bytes big, and this is the first one that's available that is good enough to split. Now, we're going to follow this first available policy, but this should immediately is like, why did you pick the first one available? Shouldn't we look for one that's exactly like 60 bytes big? And one of the areas of study within memory management is effective policies to, can you find me the best fit for this or the first available? We're going to run with like search the list and whatever one you find first that has enough space, like go ahead and split it off. But in that case, this wouldn't do because it's not big enough to split, but the 300 bytes certainly is. Now what we're going to do is to split this thing off here and then mark the 60 byte thing here as now in use. It's being granted via an lmalloc. But that means it's in the wrong linked list. And so as part of the completion, the late part of finishing this lmalloc function, you will take this lower block and plop it down in this other list. So remove it from the yellow available list and add it into the used list. And that's the source of need for those linked list manipulation functions. Anytime you add something into a linked list, it always goes to the front. Thus we have a add front linked list function. And that means then that, oh, this thing goes to the front, it's linked into the used blocks, and you can return then a pointer to the user of, here's your little gray area. So as long as you stay in between that, you won't mess up any foots or heads there. Similarly, this freshly created shaved off block up here, that has the remaining 200 bytes, that doesn't exist anywhere, so it has to be added into the available linked list over here, along with adjustments to say, oh, this available list, it just grew by one, so did this, or sorry, it didn't grow by one, but the used did, but this one lost some bytes and this one gained some bytes. So the 60 plus overhead here and the 200 plus overhead over here. So consider the documentation for that series of functions carefully, the splitting parts, and then how it's used within lmalloc down here. In the event that you can't split off a block, then either you're looking at a wrongly available one, or it's possible there's not enough space in the heap to split anything off. So for instance, if I said, hey, malloc me something is 200 bytes big, we search the available list over here, be 22, definitely not big enough, 16, not big enough, 100, not big enough for 200, so we're stuck. In some cases, malloc might return null, but in our case, we'll expand the heap at that point to create a larger available block to fulfill the memory requirement. So the counterpart to splitting is merging. And this happens during a call to free. So we'll start just with the merging semantics here. So suppose some user has a block over here, and so they have a pointer to 60 bytes. They say, hey, free this thing. I don't need it anymore. You can find the blockhead just by doing a little pointer arithmetic. User pointers at the gray spots, back up the size of a head, and voila, you've got the head here. And find that, oh, that's in use. We're freeing it, no problem. So mark it then as available. And then poke around and say, hey, if the things that are next to me, those are available, then I could actually merge this 60 byte block into something that's a little bigger. Now, in this first case that's considered here, it's not possible because you look up and say that's in use, no chance to merge there. Look below, that one's still in use as well. There's no chance to merge there. Importantly, this does not traverse any linked list nodes. Rather, it says, here's a head, go to the block below it, or go to the block above it. And so to that end, there's no linked list manipulation for that part to sort of look around to see. There is linked list manipulation in that if this is the block that's getting freed up, then it comes out of the used list and into the available list. So is in this gray used list and goes into the yellow available list. However, there are some cases in which it's possible to merge blocks together. So for instance, if this is the block that is being freed, not right here, 60 bytes, you can see the one below it is also available, 90 bytes. So we'll free it, so this becomes yellow, and then look around and say, hey, I look up and I can't merge there, but I can merge with this one below. And that will recoup some overhead to say, oh, it's the 60 plus the 90 plus I don't need this middle head-foot pair anymore. And so the merging means that there's now one additional, I would go from an available list of 5, which has this yellow one in it someplace, to 6 over here, but then back down to 5 because I can merge these into one bigger block. And that would make it possible to then grant a larger malloc. That 90 and 60, that wouldn't be enough to grant a malloc of 100. However, 190 bytes down here is easily able to grant that. And so this reduces the amount of heap fragmentation that happens, and is sometimes referred to as coalescing blocks together. I'll just generally refer to them as like, oh, you got to merge these two together. Now you can envision other cases where like, oh, this one is being freed, this one's in use, but this one's available, and so I'd merge these two. And finally, if both of these are available, I can merge all three together in that way. The only function that you're required to implement is to merge block with above. As in take a block like this one and see, can I merge with the one above it over here? And that's because generally as I'd free this one and convert it to available, you can just do a little pointing arithmetic and say, try to merge this one with the one that was just above it. This doesn't need to iterate or anything, because if you maintain the constant that there are never any two available blocks that are adjacent to each other, if they're always merged aggressively in that way, then you only need to look on freeing something left or down one block and then up one block and perform any merging that is necessary there. Now, if this all sounds like a lot, these functions are all of like 10 lines long. They involve a little bit of pointer arithmetic and some reasoning and logic, but there's a fairly good set of commentary in the outline file on how to go about doing these things. So look at the diagrams, perform linked list manipulations, and generally just use caution, and you should be fine. This can probably be completed in like 1 to 2 sittings or so of a couple hours a piece if you're efficient on it. Okay, the last part of this is to expand the heap if needed. And in the event that someone mallocs all of the space that's in the existing heap and you run out, then you'll need to just start plopping some pages down here. This will make use of the mmap function. And mmap generally has a use case that fits very nicely into this. We talked about it in the context of virtual memory. If you start the heap at some location and track this is where the heap ends, and access to things beyond that would be out of bounds, then you can say, well, actually, I want that to be inbounds now. And so make use of mmap to say, here's where the heap ends. There's a pointer to that in the lmalloc struct. I think it's up here. This is the L control here, heap end. So take that, mmap some space up there, some number of new pages, and this will extend the heap. Of course, you then want to adjust, I have more bytes in the heap, and I'll want to change my heap end so it actually reflects like this is off the end of the heap now. There's some commentary down, let's see, expanding the, on how to go about that. Just bear in mind that mmap itself can be called with some number of bytes, and you want to make that a multiple of 4096, the size of pages. There's a pound defined for that there. And after you malloc these additional pages of memory, you'd want to do things like, oh, I've got to plop down an available block there because it's there. And potentially, if the very last block in the heap is free, like it is here, this one's available, and I plop down a new available block over here, then attempt to merge those two so it's one big block. And generally, this will happen then in the case that I malloc something, there's not enough space because I searched the whole heap for this thing using my now find next available function. And as I run out of space there, I'll malloc some more pages and then use the new now available space that's been malloced on for that. Okay, that's probably enough commentary on this. Have a look at the pictures, ask questions, and we should be good on that. The second problem is much easier to describe, although somewhat less sort of straightforward to implement because it'll involve maybe just a little bit of creativity on your part. So this is a classic optimization problem where we are going to give you some provided code that runs too slow and then ask you to implement a faster version of it. The problem that's solved by the provided code is to sum the diagonals of a matrix. Now, if you've not worked with matrix before, then you may want to do just a little bit of review on them. They tend to be divided by rows and columns, a two-dimensional table of numbers, and there's a data structure that's provided in the code pack for the project that is what you should use for the data structure of this 2D thing. It's just like the ones that have been in the recent labs and the lecture discussions, where it's like, oh, got one big giant array where everything's laid out in row major order here. Now, I should say a word on the diagonals. Diagonals are colored here, so oftentimes the main diagonals of important linear algebra. That's the one where the row and the column number are equal. So row 0, row 1, column 1, row 2, column 2, etc. Down here, colored in goldenrod here. But the terminology associated with diagonals is extended beyond that. They'll refer to lower diagonals as things that are sort of below that, and upper diagonals that are above that. And there's not a standard numbering scheme for diagonal numbers here. So I picked one that is relatively convenient, where each of the diagonals has some number, starting at the sort of lower leftmost diagonal, which is comprised just of this single lower left element. We'll call that diagonal 0, and then march upwards from that. So here's diagonal 1, which is this salmon color, and diagonal 2, which is this green color, cyans, diagonal 3, the main diagonal is number 4, etc. up to that. So generally, you'd expect 9 diagonals in a 5x5 matrix like this. The 5x5 is 0 inclusive there. And the number of diagonals then is something like the number of rows plus the number of columns minus 1, if I remember right, something like that. And that's for a square matrix, which is all that we'll deal with. The idea of computation of this is just to sum up the diagonals. So sum up in some place these sort of dumb, this 0th element here and the 0th diagonal is 20. In this 1th, I'll add on 15 and 21 to get 36, and 10, 16, 22 to 48, etc. So there'll be 9 of these here, and these will be stored in some sort of an array or vector, if you will, which is just a one-dimensional array of numbers. So there's code provided to do just that. It's called SumDiag based normal, and it does the really sort of dumb thing of if I were human, I'd just scan along diagonals like this, like adding up numbers, and this is reflected in code. There's a numbering scheme for the lower diagonals, a numbering scheme for the upper diagonals, but generally each of these outer loops computes one diagonal by here and here, and each inner loop is used to visit elements within the same diagonal and add on their contents to some vector element here, which is summing up those. So the base interface for this thing is just here's a matrix. Plop down the sum of all its diagonals in this vector, and you can access those using matrices that are over here, operations like mget and vget and so forth. Okay, so with that in mind, this thing is going to be terribly slow, or at least not particularly performant. Certainly easy to get right, but the fact that you are going along a diagonal, so not across a row, which is the most efficient access pattern for row major matrices, the fact that you'll go from this diagonal element to this diagonal element, which is a big jump in memory, and then to this diagonal element, which is a big jump in memory, and then jump back to compute the elements of 5 and then 11 and then 17 and so forth. All of this should scream poor cache performance, that this is just not going to clip along at the speed that one might want if you were interested in speedy code for it. So your job is to write a faster version of this. And generally the optimizations for this fall along 2 lines, and I'll jump down to those optimization suggestions. The first is to reorder the memory access pattern so that it's as sequential as possible. And likely, if you don't do this, any further optimizations you might seek to implement, they will not produce any real benefit. Once you get the memory access pattern sorted out to visit things across rows in a cache variable pattern, then the next optimization is to split up this work and parallelize it, making use of threads, the last topic that we'll talk about in lecture. Now, threads are nice because if you spin up a number of threads and there are available cores, available processors on which those threads can run, they can run in parallel. And so there's a theoretical possibility that, I can divide this into 2 chunks and do them in parallel, and that might get me a 2x speed up. This doesn't happen in practice too often, may in this case, but generally as you spin up more threads, other things sort of go sideways. They might need to coordinate, they might interfere with the caching performance of each other, but you generally get some performance benefit from them, so they're worth it to do there. Now, a few words on how this is evaluated, and then I'll offer some more tricks there. Generally, if you do those two optimizations, you should be in good shape. So you'll write your own code in a sumdiag optim function here. That's provided in the code pack in sumdiag optim.c. There's some commentary up here that we'll get back to, but this is the function down here. Generally, folks should take a sort of iterative approach to this to say like, oh, I'm going to write some code that will, I think, might speed this up and is generally correct. And then I will test it in the benchmark. And as you get a version that gets you some points, we'll see those points in a second, you might copy and paste it and then make some more tweaks or some improvements or into here. Then change this from version 1 to version 2, retaining your old version and using the new version. And this should sort of progress then. So I'm going to copy and paste and move forwards. It's fine if you just want to include the most recent version. That was the fastest for you here. But I found it useful to experiment with this. So this architecture is set up expressly for that part. At any rate, the code that's right here, you might start by like dropping in the baseline version over here, this sum base normal. So let me just grab over here this thing, and we can copy and paste it over here, my version 1, like so. Okay. And then the primary evaluation for this, now that I've set it up, so I remake this thing. Let's see, I did something wrong here. Oh shoot, okay. Did something wrong there and got too much code, so let me grab the other one here. So it's here. I don't want the debug version though, I want this version up here. That, and then maybe paste that in here. Here's my version 1. Okay, how do you like me now? It's good. Okay, so the primary criteria by which you'll be graded on this is to run this provided benchmark. Now this thing has a bunch of quirks to it, but it's worthwhile just to run this like straight out of the gate here. The way that it evaluates things is to run your code with this sumdiag optim version, but also to run the baseline version, and then compare the speeds of each of those. So for instance, you can see over here that the time it took the baseline version is this 0.036 seconds, and the optimized version is 0.23 seconds. That got me a little bit of speed up. Not sure exactly why, but things are a little bit funny at this sort of smallest level over here. That earned a small number of points. Generally, the number of points you earn is contingent on the speed up, along with it's scaled by some factors that relate to the size of the matrix that's being run, so 1024 in this case. The larger matrices and better performance on those is worth more credit. Now you can see that for my stupid version over here, where I just copied and pasted the original version, it starts running at almost exactly the same speed as the original, so 0.41, so it's like actually a slowdown here. 1.10 speed up. What I'm looking for is like a 1.5x speed up, or 2.x, so I went twice as fast with the version over here. And you can see that this other parameter over here is this optim version is called with a number of threads that it should respect. And so should launch some number of threads that's indicated over here, and that's used then to dictate the speed up that's over here. So it might be called with just a single thread, and then 2 threads and 3 threads. It's 1, 2, 3, 4, because that's what the Grace nose had over here. So right now I got a piddly 1 point out of 30, which is, basically nothing at that point. But hey, all I did was copy and paste the provided slow code in, so I don't really have any expectation that it would go much faster than that. The other thing that's worth pointing out is I'm running this on my home computer right now, Val, and you can see there's some warnings issued over here that I need to be running this instead for proper evaluation on an odd numbered Grace node. So as you SSH into Grace, it puts you on some node like 3, 4, 5, 6, 7, 8, 9, 10. The odd numbered Grace nodes are a little bit faster, and so that's where we'll do our benchmarking. If you happen to land on an even numbered one like 4 or 5 or 4 or 6, then just SSH to like Grace 5 or Grace 7 or Grace 9, and that will give you a higher fidelity or sort of more accurate there. But warnings will go away. I should mention that the slower Grace nodes, they're much easier to make your benchmark results look good, so make sure to respect this. It's fine to sort of test out code at home or on some of the even numbered Grace machines, but ultimately the TAs are going to evaluate this on an odd numbered Grace machine under low load, and so you'll want to know that your code screams along fine on those there. So warnings up front and warnings at the back over here indicating I'm running on the wrong host here, so find a good one there. A couple notes in terms of that evaluation. There's some test runs given over here. For instance, warnings given if I logged into the wrong node or running at home, some partial credit. Full credit is possible by implementing a couple of the optimizations that I talked about a second ago, and there's one that's given down here. Generally, we're looking for about a score of 30 or thereabouts, and if you exceed that, then we'll just sort of round back down to about a 30 out of 30 here. And in my stock implementation of this, doing just these two things that are mentioned down here, this was all it took to get consistently a 30 out of 30 on the points here. You can achieve higher performance on this, and doing so will garner some makeup credits. So I think you have to exceed 35 points and then to get a +5, and if you manage to exceed 40 by implementing some other optimization tricks, then that's another +10 makeup credit for you. If you're looking for inspiration, Brian O'Harlan has a whole chapter on different kinds of optimizations that you might try to make use of. And the compilation on the in the makefile is intentionally, it has disabled a lot of the compiler generated optimization, so it's doing debug level optimizations. You're not to alter that. In fact, if I change this to 03 over here, then likely I'd get a whole bunch of speed up, but that's because the compiler did a bunch of stuff for me. The point of this exercise is to study a little bit speed ups that you might institute in your own code to see how that looks and what kinds of transformations the compiler might be performing for you. So don't mess with the optimization options. We will not mess with them when we evaluate your code. So if you're like, oh, I got 500 out of 30 on this because I changed this to turn on a bunch of optimizations, that's great for you. But when we run it, we'll be running it with debug level optimizations. So make sure that you practice on that and have your code reflect the ability of the Grace compiler to eke out better performance, even with these debug level optimizations. Other things to say, it's very likely that during the course of optimizing, you break the code. In that generally you have working code and you just leave it be, and trying to make it go faster means doing a bunch of tweaks that will start producing incorrect results. The benchmark provides for this and will check for it. So if I buzz back over here and do something inadvertent like maybe I forget to do whatever this part is down here. I'll make again. Let's see. Oh, it's not used there. Maybe I'll just set this thing to be +1 instead. So there's an obvious mistake over here. If I run this again, then I'll get a litany of errors over here because as this is running, the base version that is the stock code is checked against the optimized version to make sure you're producing the correct results. And failure to do so will just yield 0 credits at the end of the day on this. And to that end, it can be hard to debug these because this is a big old benchmark and you're producing weird stuff over here. So for that, there's a provided printing code over here, this sumdiag print, which can be useful. So sumdag print, if I run it, it would say how big do you want the matrix to be and how many threads do you want to run, useful for debugging the threaded stuff. In my case, I'll just say I don't know, maybe a 10 by 10 matrix with one thread. So this will print out the matrix that is produced over here by your code, as well as then show the baseline and the optimized versions. And this is where, over here you can start to see there's a problem up with this, that there's little star marked lines here. This is a diagonal element the way it's supposed to be, and this is a diagonal element the way that mine has computed it. So going across this 10th diagonal, which should probably be the upper diagonal, this 123, 34, 46, etc. down over here, because I think that's the part of the code that I intentionally muffed. That's why I'm getting this sort of off by one error, is that I added one on each of those, so that's a total of plus 9 over here, but for the 414. But at least knowing which elements are off can be extremely useful in terms of debugging. As well, if you start getting Valgrind errors, then you could run this under Valgrind. And this will tell you like, if you have out of bounds or inbounds memory accesses, and in this case I didn't have any Valgrind problems because it was numerical in nature over there. So debugging can be facilitated somewhat by that printing utility and use of it. Make use of that if you start producing incorrect code in the benchmark. Finally, then, a couple of notes in terms of your usage of threads, which will be sort of the last phase of optimizing this. That you are to adhere to a couple constraints. That there are a couple ways that you could utilize threads that don't involve the need to coordinate between threads. However, one of the goals of the class is to show just a little bit of ability to coordinate threads, in particular making use of a thing called a mutex, which we'll talk about in lecture and is demonstrated in this week's lab. This allows for a mutual exclusion, as in only one thread executes a body of code while other threads wait their turn for it. This is a required part of the project, and so you'll lose credits if you fail to make use of a mutex there. If you want to monkey around with lock-free solutions that don't require mutex, feel free to. Just make sure that the solution that you submit, the uncommented live version, does make use of a mutex. As well, avoid the use of global variables. It's extremely tempting in threaded code to start making use of global variables, as all threads are able to see them. They share all memory out of the gate. However, if you're going to write library code that others would use, and you want it to be sort of reentrant in a way that, I can call it here in one of my threads, and it spins up multiple threads, and I can call it again here in this other thing, then the code that you write needs to avoid the use of global variables, which will be a point of contention for anything in your library code that's there. This is demonstrated in the code that's provided in lab this week, lab 13 on column summing. And so utilize structure that's very similar to that, where you create a context of sorts that gives a thread a unique numeric ID, tells it how many threads there are, and passes in any references to like matrices and vectors that are needed to get its job done. This will enable you then to launch that code from any other thread, and is generally better software engineering practice, even if it's a little bit more overhead in terms of writing there. Okay, I think that's about all I want to say about this part. Generally, folks have fun with this because it's not too hard to get full credit on it, and then it becomes a game of who can get 45 out of 30 or 50 out of 30, and so have fun with that part. As you would make the makeup credit portion of this, it will become very obvious that you've scored that, because the printing over here will change ever so slightly. This is our last project. And I should say the optimization thing here, that probably take you again 1 to 2 sittings of an hour a piece to get the baseline version up and running, to get some optimizations implemented, and then to crank it out, and you can dump some more time into it if you really want that makeup credit. But based on the templates that are provided, this should be easily doable within the time limit that we have, which is due on the last day of the classes. All right. I'll sign off at this point. Good luck to all of you. Happy hacking, and I'll see you in lecture.